everyone. Today we discuss about understanding numbers. We try to understand numbers. What portion we cover today? The decimal part and the integral part of a number that we see, and also the integral part of a number has got different weights. The weight of a number is its position with respect to the decimal point. That we will see that the other thing which we cover is going to be what's a number on a number line. The basic concept of a geometry, which is the smallest geometrical figure, is a point. So that point represents what? A number on a number line. So we will see one number line. We just put one number line. Say this one. This is a line X. Or a line X. On a line X, how do we put numbers? How do we represent numbers? That we are going to see. The other thing which we try to see is how many numbers we can get in between two numbers. This concept we try to define. Infinitely many numbers we can find in between two numbers. Likewise, on a number line, as you go to the positive side, to the right, you have got infinitely many numbers up this area. Same thing on the left side, on the negative side as well. As you move on, you have infinitely many numbers, uncountable. The same thing is true in between two numbers, say 1 and 2. You have infinitely many numbers in between this. That concept we will see. The other thing which we see, what is addition operation, a subtraction operation, and multiplication, and also division. We have to see what are numbers. We will try to see what are numbers. Numbers are in fact a set of collection. So we name them natural numbers, whole numbers, integers. We will see what these numbers are. The other thing, in integers we can have a positive integers, negative integers, non-positive and non-negative. We will see once we finish about integers. We will discuss about rational numbers and irrational numbers. These are the two major sections of a number. In fact, any number is either rational or irrational. Then the set of these two, when we unite them all together, it gives us real numbers. That's all numbers. Any number is a real number at the end. So that we are going to see. In numbers, we can have decimal-wise, terminating decimals, repeating decimals. Others repeating and terminating, but there are also decimal numbers which are neither repeating nor terminating, which fall into irrational number that we will see in detail. I'm just only highlighting which topics we are going to cover. When we talk about repeating, it's not only decimals that repeat. Certain division factors, as we have seen here, these things are also repeating. 2 plus 1 over 2 plus 1 over 2 plus. This keeps repeating forever. Will it be rational number or irrational number? We will cover it in detail. I'm just highlighting what portions we cover. Then we will see what are square roots and cube roots. Which square roots are rational numbers? Which ones are irrational numbers? That we cover as well in our today's portion. Let's go back to now page number 1 and start the lesson of the day. This is all about understanding numbers. Numbers do have the integral part and the decimal part. What makes an integral part is exactly to the left side of the decimal point. The other side, which is the right side of a decimal point, are the decimal parts. So the position of every number is its weight, how big it is, or what it represents depend on the position based on the decimal point. Here, the integral part of this number, 1248, decimal 246, it has an integral part, 1248, and it has a decimal part, 246. The decimal part is after the decimal point. The integral part is the one which is on the left side of the decimal point. We can call it before the decimal point, no problem. The one which is very close to the decimal point is a units. The next one, tens, hundreds, thousands. It keeps on like that. 10,000s, 100,000s, so on and so forth. On the right side, the first one is tenth. Tenth. This one is tenth, not tenths. Hundredths, thousandths, like that. These are where it is located based on what with respect to the decimal point. Its position or location is called the weight of the number. In this same number, 1248 decimal 246, the more to the left of the decimal point, the higher the weight of the number, this side. So the weight of 8 is, it is the units for the first one. Then after, the tens. Number 4 is the tens. Let's go back to the first page. This one here. 8 is the units, 4 is tens, 2 is hundreds, and so on and so forth. What does it mean by units, tens, hundreds of position? That we'll see it in more details up here. When we expand and see this number, 1248 decimal 246 is 1 times, how many numbers it's got on the right side of it? A total of 3 numbers are there. 1 times 10 to the power of 3. This one here. So this is a weight of 1 is 10 to the power of 3, which is thousands. Number 2, we'll have 2 times 10 to the power of 2. Number 4, we'll have 4 times 10 to the power of 1. 10 to the power of 1 is just 10, which is tens. Number 8, we'll have 8 times 10 to the power of 0. Any number to the power of 0 is just 1. It means 1. Except for the fact that 0 to the power of 0 is not defined. So 10 to the power of 0 is just 1. In my next expression, I'm going to write this one, just number 1. Then another one is here, 2 to the power of 10 to the power of 2 times 10 to the power of minus 1. Now, what is the smallest number after 0 is minus 1? It comes to be negative here, 0 minus 1. This is the weight of 2 is 10 to the power of minus 1, or it is, what is 10 to the power of minus 1 is 1 over 10. Tenth. This is a tenth power. The next one, 4 times 10 to the power of minus 2, hundredths. This is defined down here, so no need to write it again here. So 10 to the power of 1, I give it a 10. 10 to the power of 0 is 1. It's a definition. It takes like a definition. 10 to the power of minus 1 is 1 over 10 to the power of 1. We invert it. We put it down because of this negative exponential. When it is down, 10 to the power of minus 1, the negative 1 here will be positive, which is 1 over 10, which is tenth. 1 over 10. 1 divided by 10 is 0.1. 10 to the power of minus 2, which is 1 over 10 to the power of 2, which is 1 over 10 square. 10 square, we can say it in other words, which is 1 over 100. That's why we call it hundredths. The placeholder is hundredths. Another one, 10 to the power of minus 3, 1 over 10 to the power of 3. Change the sign here, negative to positive as it inverts down there. So it's going to be thousandth placeholder. This what it is, just to understand the position holders for the numbers. Here it comes now in the expanded form. 1248 decimal 246. 1,000. 200. 4, which is 40. 4 times 10 and 8. You can simply see it, 1,248. 1,248. The decimal part, 2 times 0.1. 4 times 0.01, 6 times 0.001. It's just tenth, hundredth, and thousandth. It's a decimal place here. It's how we expand it and see the power of each and every number. So when we simplify it up, this part here, it's going to be one. This one is 1000 here, 200 here, 48.246. We can add them in the downwards form. When we add, what we have to do is we align the decimal points here, 1248, then decimal 2, decimal 04, decimal 006. Whatever in front of this decimal is nothing but is 0. On the right side of this decimal point as well, zeros. These are zeros. I just keep it open. Nothing means you can put 0 to see a better alignment of the numbers. Just this is to make it aligned, but nothing else. You put 0 here or there, has no values at all. So when you add them in the downwards by aligning the decimal point up here in the center, you get the same number, which is 1248 decimal 246. Let me clear what I have added now. Okay. More example. 489 is 489. 209 is 200. 0 is 0 and 9. 209. The weight of 2 is hundreds. The weight of 0 here is tens. The weight of 9 is units. Here, another example. In 382, the value of 3, or the weight of 3 is, the value of 3 is 300. The weight is 100, its value is 300. The value of 8 is 80. And the value of 2 is just 2. It's in the units position. So the whole number is 382. Which digit has the greatest weight or value in 459? 4 hundredths. So 4 is having the highest value here, 200. 2 is in the position of 100. That's just how the position of it to determine the values. 1486, 1 has the highest weight or value here. Another one, definition. A unit is a 1. Tens is 10, hundreds is 100, and thousands is 1,000. Some ways of numbering. For example, some ways of numbering, in other ways of calling numbers like 2000. What does it mean by a 2000? We just put 20 times 100. Simply it means 2000. So a 2000 is 2000. What about a 1500? A 1500 is 15 times 100, which is 1500. You can call it 1500 or you can call it 1500. This is another way of saying it. What about 500s? 500s. It is just 500. What about 2000? 2000 can be 2010. I mean 210. 2000 is 210, which is 200 tens. Sometimes how many tens we have in 2000? How many tens we have in 2000 is maybe a question. How many tens we have in 2000? Just put 10 separately here. 200 times 10. 200 tens we have in 2000. 2000 is how many units we have in 2000? 2000 is 2000 multiplied by 1. 1 means units. 2000 units or 200 tens or 20 hundreds. Also another possible way of saying it. 20 hundreds. We can also say 20 hundredths. Let me clear some of these markings and we go to the other page. 2000 is 20 hundredths. So I've said it already. Another example here. Which of the following has same value as 5 hundredths? 5 hundredths, you put just 5 and 100. 5 multiplied by 100, which is, you can write it 500. Which is, what is exactly 500? Is 50 times 10. 50 tenths. 50 tenths is the same as 5 hundredths. Or simply you can say 5 and hundredths. It is the same thing. What about 400 units? Units means 1. 400 units means 400, or 400 multiplied by 1, which is 40 tenths, or 4 hundredths. It's another way of saying it. You can say 40 tenths, you can say 400. 400 units. Alright, let's go to the next page. Now, what's the value of 9 in the following numbers? 189. The value of 9 is units, which is the last one. So 180, 80 is tenths, and 9, 189. So 9 is in the position of the units. What about 918? 918. It means 900 plus 10 plus 8. This number 918 is 9 in 100 position, 80 in the tens position, and no, sorry for this one. Let me clear this one. Okay. Let's come back to 1 times 10, and 8 is in the units. So it is 9 in the hundreds position, 10, 1 in the tens position, and 8 in the units. Another example here, 891. We are just checking the position of 9 as per this question. 8, 100 position, 90, 99 in the tens position, and the last one is 1. So 9 times 10 is in the tens position. What about the value of 5 in the following expression? We just put it in the expanded form and we see 6 times 10 to the power of how many numbers it's got here? 2, 3, 4, 5 number. 6 times 10 to the power of 5 plus 2 times 10 to the power of 4 here plus 5 times 10 to the power of 3. Now we are asking for the 5. 5 is in the thousands. Thousands. That's the thousands position. Alright, let's go to the next page. This understanding numbers will help us in more advanced algebra things. That's why we have to see from the basics of numbers. So numbers, what are numbers? We can put them simply on a number line. These numbers are integers here, but what are integers? We will further see them, no problem. But just see, there are pointers on a number line. This is also the basics of geometry. A point is the smallest geometric figure. That we will see it in my geometry channel. So this one is just a single point represents a number. For our simplicity, we start from 0 here. From 0, we go to 1, 2, 3, 4. Each and every one is a point on a number line. So this is just by agreement. As we move that way to the right, we go more and more positive. Then we have also the other side, which is negative. Negative 1, 2, 3, and so on and so forth. It goes to a larger number in the negative, this side, very large number in the positive. These are the points which represent a number. So we have two numbers, number 1 here, number 2 here. How many numbers we can have in the one which is in between these two numbers? We know at least one number, which is the average of the two. The average of the two here, we can have half. How do we get that one? We will further see. We still have more and more numbers in between. There is always one number between two numbers. Likewise, there is always a point between 2 points. Repetitive application of this same theory tells us infinitely many numbers exist in between two numbers. Infinitely many. We have one number here in between these two, this one. Now between these two and these two, we have one here. What about between these two and two? We further have one here. It keeps doing that. So infinitely many numbers exist in between two numbers. So here, say we have number 1 and 2. So we have number A. A is 1 plus 2 divided by 2, which is the average of the two. Add the 2 and divide it by number 2. So it is 3 divided by 2, 1.5. So we have 1.5 here. Take 1.5 here. And then between 1.5 and 2, we have another number. 1.5 plus 2 divided by 2, which is the average of the two. Which is here 3.5 divided by 2, which is 1.75. Now we have here 1.75. What we have again between 1.75 and 2? We have another number, which is 1.75 plus 2 divided by 2. We keep doing this one forever. So we have infinitely many numbers in between two numbers. That's the conclusion where we reach to. And so on and so forth. A number line contains infinitely many numbers on a number line. To the right, positive side. To the right means a positive side. To the left, a negative side. And even between two numbers, we have infinitely many numbers. What is simply adding? Let's define it and we carry on. A successive increase on a number line to the right side is adding. 2 plus 4 plus 6 is nothing but jump 2, again jump 4, again jump 6. A total jump made is going to be 2 plus 4 plus 6, which is 12. Adding normally starts from 0. You can add from what you have. Okay, you start from that number. If I already have, say, 4, and I have to add 5 on it, I have to jump 5 times to the right. That's true. But you simply add numbers, means you start from 0. Subtraction is just moving to the left side, but the same thing as addition, but in the reverse process. Moving to the left from where you are. 9 minus 4 means you start from 9 and move to the left 4 steps. 9, 1, 2, 3, 4. 9 minus 4 is 5. This is simple expression of adding and subtracting. 9 minus 4 is just positive 5 up here. Let me clear some of these additions and go next page. What about multiplication? Multiplication is nothing, but it is just a successive addition. 4 times 5. What is 4 times 5? 4 times 5 means 4 times number 5. Put number 5 how many times? 1, 2, 3, 4. And then you add. In other words, you can do a commutative property on this one. 5 times 4. Instead of putting 4 times 5, you can put 5 times number 4. The same result you will have. So 4 times 5 is 5 times 4. For any two numbers, say A represents a number, B represents a number. A times B is the same as B times A. This property is commutative property. Commutative means you can change the position, but the value is still the same. Commutative property is true for addition also. You can add two numbers, 1 plus 2, which is the same as 2 plus 1. But commutative property, moving the position, will not work for subtraction and division. We don't do that one for subtraction and division. That's why we call it addition is commutative, multiplication is commutative. But the other way around, it doesn't work for subtraction and division. It doesn't work. They are not commutative. When something is true, what we mean, it's always true. if it is sometimes true, in mathematics it is not true. It has to be true all the time. Even there is one case in which that makes it false, then the whole statement cannot be true. Okay, we go next page now. So here again subtraction. 5 minus 2, start from 5, move to the left 2 places. 5, 1, 2 places, which is 3. What about 2 minus 5? Start from 2, move 5 times. 1, 2, 3, 4, 5, which is minus 3. So 5 times 2 is different from 2 minus 5. That's because subtraction is not commutative. It doesn't fulfill the commutative property. Reverse operation of multiplication is a division. It means what? In multiplication we know 4 times 5 means put 5 how many times? 4. Or you can put 4 5 times. This is both 20. This is in multiplication. What about 20 divided by 4? It means 4 is a placeholder here. You have 4 spaces here, and a value 4 can be distributed equally in these 4 places. And how much each place will hold? That's the question. So each place will have here to hold 5. So 20 divided by 4 is just 5. Once again, back to numbers. Numbers are here. We can put them on a number line. And we put 0 here. And then 1 unit we can jump here. I'm putting only the integral parts of the numbers. There are also fractions, such as half is here, 1.5 or 3 over 2 is here, and so on and so forth. A lot of numbers are there. Infinitely many numbers are existing just in this area itself. But we are only putting the integral parts of the numbers to the positive side here, to the negative side here, and 0. 0 is not positive, 0 is not a negative, it's just a 0. So these ones are 0 on the number line. So on this one, there are natural numbers. The symbol for natural numbers we put n. Natural numbers, also called counting numbers, are those which we naturally use them to count objects, such as 1, 2, 3, 4, and so on and so forth. So numbers that start from 1 and it keeps moving to the positive side are natural numbers. The symbol for them is n. The next set of numbers is whole numbers. Whole numbers is natural numbers, but it adds what? 0. It includes 0 as well. All the way from here is whole numbers. From here is a natural number. So any natural number is part of the whole number, in fact. So whole numbers are natural numbers and 0 is included. So whole numbers, symbol for whole numbers is W, which is 0, 1, 2, 3, 4, so on and so forth. There are numbers. Other numbers are integers. We put a symbol for integers is Z. These are the integral parts on a number line, not fractions. So integers are actually what we start with here. These are all integers. So the natural numbers, the whole numbers, and the negative parts of this integral number all together are integers. So no fractions or decimals here in integers, which cannot be simplified as integers. Some fractions could be simplified as integers, such as, one example I can give, 4 divided by 2. Looks like it's a fraction, but it is just 2. 2 is integer. Okay. So set of integers, which is z, letter z, these are the set of integers. Oh, so integers do have positive integers, this part here, negative integers, this part here, and zero, this part here. We can call it a positive integer, a negative integer, and a zero. These are all sets of integers. But what about non-negative integers? Which are non-negative integers? These are non-negative integers this way. Which ones are non-positive integers? These are non-positive integers. So in non-positive integers, 0, -1, -2, -3, -4, and like that. In non-negative integers, you start again from 0, 1, 2, 3, and so on and so forth, etc. So z plus here, z plus means positive integers, which is exactly the same as natural numbers. Z minus is negative integers. More on integers. We have positive integers, now we know them. We have negative integers, now we know them. We have non-positive integers. Non-positive integers, not exactly the same as negative integers, but negative integers and zero. So in non-positive integers, you keep doing it, all negative numbers, and you end up at 0. These are non-positive integers. What about non-negative integers? Non-negative integers start from 0, 1, 2, 3, etc. These are non-negative integers. It's already defined actually here. You can see them. So z plus means positive integers, which is exactly the same as natural numbers. Z minus negative integers. Z plus none. Non-positive integers. These are the negative integers and 0. This is a union symbol. We can see it in set theory. Z minus none. Non-negative integers, 0 and positive integers, which is exactly whole numbers. Whole numbers, you remember, whole numbers is 0 and 0 union with the natural numbers. These are natural numbers are those counting ones, the one which we used to count, right? This way. So all in all, the whole numbers, the set of numbers from 0, 1, 2, 3, 4, and so on and so forth. Rational and irrational numbers. Actually, the whole picture of numbers fall into two major groups. One is rational, one is irrational. We talk about numbers, but one is included in the other. For example, when we talk about natural numbers, those are also whole numbers, but natural numbers are whole numbers in which 0 is also added in it. So once we are in whole numbers, we come up to integers. Whole numbers are all integers, but integers include also the negative parts. That's how it is. So now at the end we have only integers, in fact. So integers, again, are used to define rational numbers. Rational numbers are a fraction of two integers in a division way, a division of two integers. So here, it's not only that actually, that and plus more. So integers, a number, say n, is a rational number in which a symbol for rational number is q. Keep in mind that. That means n, or this rational number is, or it can be expressed as a fraction of two integers, where a and b are integers. But we cannot divide any number to 0, but b cannot be 0. That is just a fact. 0 is such a tricky number. It will have exceptions in different mathematical expressions or operations. Any integer is a rational number. Any integer is a rational number. It's just like a natural number is a whole number. A whole number is an integer. An integer is a rational number. This is the order it has to go through, always true. But the other way around is not always true. We cannot say a whole number is a natural number. This is false. That's because in whole number, what we have is 0 added, 0 included. Now here, any integer is a rational number, yes, because an integer too can be expressed as a fraction of two numbers, two integers at the same time. 2 is 2 divided by 1. 5 is 5 divided by 1. Minus 4 is minus 4 divided by 1. These are a fraction of integers. Any fraction of integers is a rational number. Integers can be expressed as a fraction of integers, true. Uh, we have a name for it. The upper part is a numerator, the lower part is a denominator. Let's go to the next page. Another form of rational numbers. Another form of rational numbers is terminating decimals. Terminating decimals are rational numbers because they terminate, so they can be expressed as a fraction of integers. 2.4121, it is a terminating decimal. It terminates, it ends up here. Good. Now it means 2.4121 divided by 1. But still, it is not in the expression of integers because the upper part has got a decimal section. We have to eliminate that one. How do we eliminate? Move the decimal point to the right. 1 times means when you multiply it by 10. 2 times when you multiply it by 100. 3 times it can move when you multiply it by 1,000. Here 10, 100, 1,000, 10,000, whatever. The more you multiply it, it keeps moving forward. When you multiply it by 10, it moves here. 100 moves here. After 100 you have 1,000, moves here. After 1,000 you have 10,000, moves here. It keeps moving. Let's see how it is in the next example. 24, when we make it 24, when you multiply the upper numerator by 10, you need to multiply by the same value to the lower, the denominator. You cannot multiply only numerator and or only denominator. In that case, you change the value. Without changing the value, you can multiply it by the same number. Both numerators and denominators means you multiply it by 1. 10 by 10 means just 1. You can multiply any number by 1 is a number itself. The value won't change. That's how we have to apply now. So, in general, this number 2.4121 means what? 24121 divided by 10,000. We can express it this way without changing the value. Now we know the upper part is integer. The lower part is integer. So both numerator and the denominator are integers, these two numbers. And hence the number 2.4121 is a rational number. A rational number is any number which can be expressed as a fraction of integers. So that number is rational number. What about 4.212? Yes, it is rational. You can multiply upper side by 1,000 and lower side by 1,000, which is a numerator and denominator. Then the number can be 4212 divided by 1,000. Is 4212 an integer? Yes. Is 1,000 an integer? Yes. So this number is a fraction of two integers, then it is a rational number. So 4.212 is a terminating decimal number, which is rational. Same example here. 6.4214. Terminating decimals are all rationals because we can express them as a fraction of two integers. Okay, we go to the next page. Non-terminating but repeating decimals are rational numbers. When we say non-terminating but repeating decimals, it means we can write them in the forms of fractions of two integers. Then these are rational numbers. We can say example. What is 1 divided by 3? Of course, 1 is integer, 3 is integer. So 1 divided by 3, or 1/3, we can call it, is a fraction of two integers. So this is rational. Now, when we divide 1 by 3, actually, we are going to find 0.33333. This is non-terminating, but repeating number 3 all the time. 3 repeats forever. This 0.3333, as it is repeating, it is irrational because it can be expressed as a fraction of two integers. We will see more examples on that. 4.121212. This is non-terminating because there are dots here, but it's repeating. Because it is repeating, it is irrational. 6.241241. It is repeating, so it is a rational number. Another way to indicate the repeating part of this decimal, we put a bar on the top. We have here 4.121212. What is repeating is 1 and 2. So we can simply write it as 4.12. We put a bar on the top of 1, 2 means 1, 2 is repeating. 6.241241. We can simply write 6.241, put a bar on the top of 241. It means 241 is repeating. Why repeating numbers are rationals? Because we can write them as a fraction of two integers. That's the reality. Because they can be expressed as a fraction of two integers, any repeating decimal is a rational number. 1.333, as we agreed, it is simply 1.3. We put a bar on the top of 3. Let's put 1.333 here, and we multiply that by 10 to the power of 1 minus 10 to the power of 0. Remember, 10 to the power of 0 is 1. If we multiply the numerator by that number, we have to do the same for the denominator. 10 to the power of 1 minus 10 to the power of 0. We have a reason why we choose this number, in which it will be explained further. Now 10 to the power of 1 multiplied by 1.333, this is a distribution of multiplication over the subtraction. We are distributing. We multiply 1.333 one time with this first number and the other time with the second number when we distribute it. So when 1.333 multiplied by 10 to the power of 1, which is simply 10, we move the decimal point to the right by one step, and it is 13 point, the repeating part, okay? Minus, we put the minus here. We multiply it by 10 to the power of 0. Remember, 10 to the power of 0 is just 1. We multiply it by 1 means the number itself, 1.333. In the denominator side, on the bottom here, 10 to the power of 1 is 10. 10 to the power of 0 is 1. 10 minus 1 is just 9. We put 9 here. The reason why we have to multiply this repeating decimal by this number, which is 10 to the power of 1 and 10 to the power of 0, is to eliminate the repeating part. Now when we do this big subtraction, decimals will subtract, integral parts will subtract each other. So 13 minus 1 is the integral part, which is here 12. 0.333 minus 0.333. The repeating part is now identical. So if two numbers are the same, the difference between them is 0. So there is no decimal part now. So what we have on the numerator on the top is 13 minus 1, which is 12. On the denominator, 10 minus 1, which is 9. 12 divided by 9. When we divide the upper part by 3 and the lower part by 3, we will have, not this one, we will have 4 divided by 3. We will have, let me just clear this one, I wrote it 3 over 4. That was not correct. We will have 4 over 3. So now it means what? 1.333 can be expressed as a fraction of two numbers, which are both integers, 4 over 3. 4 is integer, 3 is integer. So 1.333 repeating is rational number. Let me see another example here. 2.1, but repeating part is only 4. 2.1 repeating part is only 4. I just simplified here. Now the first one is, if I multiply it by 1000, it moves 3 steps forward here, because we have 3 zeros in 1000. When the decimal point moves 3 steps forward, 2124. Then next I multiply it by 10. By 10 means it moves only 1 step here, then 21. So 2124 will have a decimal part, 24, 24, 24 repeating. That one also, 21 will have a decimal part, 24 repeating. The repeating parts will cancel out each other. Same decimals, same decimal repeating ones, the difference is 0. So 2124 minus 21 is 2103. 1000 minus 10 is 990. Now these are a fraction of two integers. So 2.1 repeating 24 is a rational number because it can be expressed as a fraction of two integers. We can create some formula for this one. In 2.124, the non-repeating part, what's not repeating is 1. After the decimal point, what is not repeating is 1. So n, which is non-repeating, 1. Repeating part, 2, 4. How many of them we have? 2. So we have 1 non-repeating and 2 repeating parts. So the number 2.124 with 24 repeating, we multiply it by 10 to the power of non-repeating plus repeating minus 10 to the power of non-repeating. We do the same, this number on the denominator side, to maintain the value, because this 2 will cancel out later and it is just 1. So 2.124 repeating multiplied by 1000 minus 10. When you multiply it by 1000, it is 2124. The repeating part is now identical. 24 and 24 and 24 will cancel out each other. Then multiplied by 10, 21. That's why 2124 minus 21 divided by 1000 minus 10, which is 2103 divided by 990. Is 2103 an integer? Yes. What about 990? Yes. The fraction of two integers is a rational number. We can have one more example of the same. 1.2413. The repeating part is 3 of them, 413. The non-repeating one is only 2. 1.2413, 413 means 1.2413. Put a bar on the top of 413. Non-repeating decimal is 1. The repeating is 3. We have 1, 2, and 3. 3 of them repeating. So 1.2413 we multiply by 10 to the power of repeating plus non-repeating minus 10 to the power of non-repeating. 10 to the power of 4 is 10,000. So 4 places to move the decimal point. 1, 2, 1, 2, 3, 4, which is 12413 minus 1 place means only 1, 2. 1, 2. Here we still have 413 repeating. Same here, 413 repeating, still there. But we don't need it now because it cancels out in the subtraction. So 12413 minus 12 is 12401. 10,000 minus 10 is 9,990. So these two are integers. Numerator and denominator are integers. So the number 1.2413 repeating is a rational number. Here we have more on rational numbers. Is 2 plus 1 over 2 plus 1 over 2 plus is repeating. Rational? Yes, because it's repeating. What about 6 plus radical? 6 plus radical, it keeps going like that. Is it rational? Yes, because it's also repeating. But to decide on that, we need to simplify and find out the value of each number, and we see the value, if it is fall into rational number or not. So most of these repeating character numbers are rationals, but to be determined after certain mathematical operations. What is the mathematical operation we have to do on this one? Just say the value, the final sum of this number is x, this one here. So as it repeats, you will see again the same character repeating as you move forward, this part. Now this part, 2 plus 1 over 2 plus is the same as the original value, x. So what's going to happen then? X is 2 plus 1 over same x there. So x is equal to 2x plus 1, because I'm sharing now the divisions here. X is equal to 2x plus 1 divided by x. At this time, we have to determine first, this x cannot be 0, because any number divided by 0 is undefined. So we have to put that note in here. Now, when we move x up here, x squared is 2x plus 1. When we move this expression on the right to the left of the equality sign, each and every term will change the sign from positive to negative. So x squared minus 2x minus 1 is 0. This is a quadratic equation. To solve the correct true set, we need to know, or we need to apply quadratic equation formulas. This section is covered in linear and quadratic equations section. We don't do it at this time, so we'll do it in the other section, linear and quadratic equations. So this number is what? This number is a rational number. After solving this quadratic equation, we will get an integer solution set, and then this is a rational number. What about irrational numbers then? If a number is not rational, then it is irrational, because every number, the symbol for irrational numbers is p. Any number is either rational or irrational. So if it is not rational, then it is rational. One of the things that makes a number irrational is when it cannot be expressed in the form of fractions of two integers, or neither repeating nor terminating decimals. Here, when I put a decimal up here, it looks like I'm saying 8 is repeating. But for a number to be irrational, it's not repeating. It goes random. 4, 1, 2, 6, 7, 8, 2, 3, 5, 4, 3, whatsoever it says. But it never terminates. Then that is irrational. Neither repeating nor terminating decimals are normally generated from radical numbers. What is exactly a radical symbol? This is the one here. And then we try to see square roots and cube roots right after this. A square root is just defined as, you just put small number to here and then put a radical sign up here. 2 is just a default value. So in most cases we don't need to put 2. If there is nothing, it means 2. That means square root. The other one is a cube root here. Let's see what makes non-repeating, non-terminating decimals to be created. Uh, Square roots, by the formula of square roots, when you have two identical numbers, consider as 1 to be freed out of that. Example, square root of 1 is square root of, you can say 1 is 1 times 1. Now you have 1 times 1, two of them here, you take one of them out. Then there is no more square root. So a square root of 1 is just 1. What about square root of 2? Can you find identical two numbers to get one free? No. What about square root of 3? No. What about square root of 4? In the square root of 4 you can have 2 times 2 because 2 times 2 is 4. When you have two of these identical numbers, one will be free. Then this is 2. So this 2 is integer. Here 1 is integer. So square root of 1 is a rational number, integer or rational number, as it can be expressed as a fraction of two rational numbers. 1 is 1 divided by 1, 2 is 2 divided by 1. This is a fraction of two integers. So square root of 4 is rational, square root of 1 is rational. But the square root of 2 and 3 are irrational numbers. What about square root of 5? Irrational. 6, irrational. Square root of 7, irrational. Let's see more in the next page. What about square root of 8? Square root of 8, as we simplify 8, 8 is 2 times 2 times 2. Now we have three identical numbers, which are 2's. So two of them can be freed. Out of these two, one of them will be freed out of the square root sign. Then the other one will remain there. So this is square root of 8 is 2 square root of 2. This is irrational. One part is irrational, that's true. And then 2 times square root of 2. This part is irrational. In this specific example, the product of these two is irrational. So square root of 8 is irrational. But this is not necessarily true that a rational number multiplied by irrational number will give us irrational. It depends. For example, 0 is rational, multiplied by square root of 2 is irrational. The result could be also rational, 0. 0 is rational. The product of one rational and one irrational number could be rational, could be irrational. It depends on the values. The square root of 9 is square root of 3 times 3. We can take 3 out. So this is just integer or an integer divided by an integer. Then square root of 9 is rational. What about square root of 16? 2 times 2 times 2 times 2. Out of these two, one is freed. Out of these two, another one is freed. So 2 times 2 is 4. Square root of 16 is 4, and it is rational. So numbers such as 1, square root of 1, 4, 9, 16, 25, 36, 49, and 64. These are called perfect square numbers, and they are rationals. Where we get perfect square numbers? We get perfect square numbers multiplying each and every natural number by itself. 1 times 1 is 1. So square root of 1 is 1. 2 times 2 is 4. Then square root of 4 is 2. 3 times 3 is 9. Then square root of 9 is 3. 4 times 4 is 16. Then square root of 16 is 4. 5 times 5 is 25, then square root of 25 is 5. 6 times 6 is 36, then square root of 36 is 6. 7 times 7 is 49, then square root of 49 is 7. 8 times 8 is 64, then square root of 64 is 8. 9 times 9 is 81, then square root of 81 is 9. So, these numbers here are all rational. What about in cube roots? 1 times 1 times 1 is 1. Then cube root of 1 is 1. 2 times 2 times 2 is 8. Then cube root of 8 is 2. These are also perfect cubes. Then these are rationals. We talk about this, the product and the sum of rationals and irrationals. We can add some more things here, some more examples. The ratio of the product of two irrationals could be irrational, could be rational. Root 2 times root 2 is, because we have now two of these same numbers, we take one for it, that's 2. The product of two irrational numbers could be rational. It could also be irrational. It could also be irrational. I can give the product of two irrational to be also irrational. Root 2 multiplied by root 3, which are the product of two irrational numbers, is root 2 times 3, which is root 6. This one is irrational. The product of two irrational numbers could also be irrational. Same, likewise, division is true. The ratio of two irrational numbers could be rational or irrational. But it is always true that the product of two rational numbers is always rational. Rational multiplied by rational is always rational. This is always true. So, non-perfect squares, non-perfect cubes. These are perfect squares and perfect cubes we talk about. Non-perfect squares and non-perfect cubes are irrational numbers. It is where we can find neither repeating nor terminating decimals. When we put them into our calculator, the calculator will chop off after a certain digit, and it gives us round of values, which does not mean these numbers are terminating. Square root of 2 is not terminating, is not repeating. So something which is neither terminating nor repeating is irrational. That's the thing. So any number which is rational united with irrational, the union of these two all together gives us real numbers. Real number means any number. Real number means any number. We can have positive real numbers. We can have negative real numbers. We can have also 0. Any number we know is a real number. That's all about numbers. Thank you very much for following up this basic understanding numbers. As we go to advanced levels of algebra, these things will apply consciously or unconsciously. We're applying them here and there. So it's a good thing to know them from the basics of that one. The more advanced things of these numbers is another subject called number theory. If you want to know more about numbers, a separate section will be there in my channel that's called number theory. So in number theory we can have more and more about numbers, but for the basic algebras, this is all about numbers, and that's just good enough to know. So just subscribe and follow to get more and more new videos as it is uploaded. Have a good time, and thank you.